this topic is about understanding logarithm as an inverse function of an exponential and using this to solve simple equations. Now, when you have a function, you have an input. Once you apply the function, you get an output. Now, if the function is, for example, multiplying by 2, so you take the input, you multiply by 2, you get the output. If you're going to go from output to input, which is reversing the order, then it's the same thing as applying the inverse function. So in this case, we'll be dividing by 2. So we know that the inverse of multiplying by 2 is dividing by 2, and we're quite confident in saying that. If we have a different function, so input and output there, let's say the function is that we take the input and we square it. Then if you want to apply the inverse of that function, we're quite confident saying that when we square root it, when we square root the output, we go back to the input. Now we know that that is the obviously inverse function, but however, we use a calculator to normally perform this. So it doesn't matter. We don't care how the calculator works it out, but we know when we square root the output, we'll go back to the input. In a similar way, when it comes to exponentials and logarithms, if you take the input and you apply 3 to the power of as a function, if you want to go from the output to the input, you need to use your calculator. But instead, the inverse function is log base 3. Okay, so the inverse of 3 to the power of is log base 3. And I need you to get confident saying that. So 3 to the power of has an inverse function of log base 3, the output. So what we know clearly from this is exponentials and logarithms are inverses of each other. Okay, so if we have log base 2 of an input is inverse of 2 to the power of. And same thing, 2 to the power of is the inverse of log base 2. Let's apply this in theory to some examples. So e.g., if we have 3 to the x is equal to 14, then because we have 3 to the power of something, the opposite of that is log base 3. So we apply log base 3 to both sides. So log base 3 of 3 to the power of x is equal to log base 3, 14. So be very clear, you apply log base 3 at the start to both sides. Now we know log base 3 and 3 to the power are inverses of each other, so they cancel each other out. So x must be equal to log base 3, 14. You can input that into your calculator using the log button. So if I input that into my calculator, I can get an answer. So x will be equal to 2.402 to 3 decimal places. Another example might be this one. So we have log base 2 of x minus 3 is equal to 7. So now we've got a log base 2 on both sides of on the left-hand side of the equation. The opposite of a log base 2 is 2 to the power of. So we apply 2 to the power of to both sides. Okay, now we know 2 and log base 2 are the same, are inverses of each other. So we're left with x minus 3 is equal to 2 to the power of 7. So x will be equal to 2 to the power of 7 plus 3. We'll put that into our calculator. 2 to the power of 7 plus 3. X will be equal to 131. Just briefly, I'll go through a log graph. So the log graph looks like this. Y is equal to log base something of x. So as you can see, it's only defined for positive numbers. Okay, so log graph, log of x defined for positive numbers. Because remember, if you think of the exponential graph, it doesn't have it, you can't have an output of a negative number. So here the input has to be positive numbers. So the input cannot be negative or 0. Now that we've gone through the theory, let's go through some examples. Okay, so first example, solve 5 to the power of 2x plus 3 is equal to 34. So because 5 to the power of something, the opposite would be log base 5. So apply log base 5 to both sides. So log base 5, 5 to the power of 2x plus 3 is equal to log base 5 of 34. Which means 2x plus 3 will be equal to log base 5 of 34. Which means 2x, if we got 2x plus 3, you have to subtract 3 from both sides. So log base 5, 34, take away 3. And once you divide by 2, you get log base 5, 34, take away 3, divide by 2. Next example, we've got log base 4, x to the power of 5 is equal to 10. Because we got log base 4, we have to do 4 to the power of, because that's the inverse of log base 4. So 4 to the power of log base 4, x plus 5 is equal to 4 to the power of 10. Remember, applying both operations to both sides. These two cancel each other out, so all I'm left with is x plus 5 is equal to 4 to the power of 10, which means x must be equal to 4 to the power of 10 minus 5. Okay, these are all using the unknown is in the index, so all similar questions. Okay, let's start with the first one. A, 3 to the power of 4x is equal to 2. Because 3 is in the base, I need to apply log base 3 to both sides. So log base 3, 3 to the power of 4x is equal to log base 3 of 2, which means 4x is equal to log base 3 of 2, which means x will be equal to log base 3, 2, divided by 4. Let's go to B next. 5 to the power of 2x minus 1 is equal to 10. So because it's 5 to the power of an unknown, I need to apply log base 5 to both sides. So log base 5, 5 to the power of 2x minus 1 is equal to log base 5 to the power of 10. So log base 5, 10. Okay. Undo, so oops. Where are we? Okay, so these two cancel each other out, that's the whole point. So we've got 2x minus 1 is equal to log base 5 of 10, which means 2x is equal to log base 5, 10 plus 1, because we have to add 1 to get rid of it on the left-hand side. All we have to do now is divide by 2, so we get log base 5, 10 plus 1, divide by 2. So that would be B. Let's go to C now. Here. 5 to the power of 3x minus 6 is equal to 2 times 5 to the power of x plus 4. Now I can see I've got base 5 on both sides, so what I'll try to do is get everything with the base 5 to the left hand side. So I would do 5 to the power of 3x minus 6 divided by 5 to the power of x plus 4 must be equal to 2. Now the laws of indices tells me I can obviously simplify this. 5 to the power of 3x divided by 5 to the x is the same thing as 5 to the power of 3x take away x, which is 2x. Maybe I should write an intermediate step. So this is the same thing as 3x take away 6. Because it's dividing, we subtract the indices, is equal to 2. So I end up getting 3x take away x, which is 2x, minus 6 take away 4, which is minus 10, is equal to 2. Now we've got in the form that we're used to. So because it's 5 to the power of, I need to do log base 5 to both sides. Log base 5, 5 to the power of 2x take away 10 is equal to log base 5 of 2. These two cancel out, So all I'm left with is 2x minus 10 is equal to log base 5 of 2. 2x is equal to log base 5, 2 plus 10. So x must be equal to log base 5, 2 plus 10 divided by 2. Okay, let's do the last one here. So D, 6 times 7 to the power of 6 take away x is equal to 5 times 7 to the power of 1 plus 2x. Now, everything with base 7 should go on one side, and everything without base 7 should go on the other side. So I'm going to divide by 5 to both sides, so you get this. On the other side, I'm going to get 7 to the power of 1 plus 2x divided by 7 to the power of 6 take away x. Okay, this is the same thing as 6 over 5 is equal to 7 to the power of 1 plus 2x. Because it's base 7 and we're dividing, it's the same thing as subtracting the indices. So I get 6 minus x, which means 6 over 5 is equal to 7 to the power of 1 take away 6 is minus 5. And 2x plus x is 3x. So I get 3x minus 5. Because it's 7 to the power of, I need to apply log base 7 to both sides. So log base 7, 6 over 5 is equal to log base 7, 7 to the power of 3x minus 5, which cancels out. So I've got log base 7, 6 over 5 is equal to 3x minus 5. If I add 5 to both sides, I get log 7, 6 over 5 plus 5 is equal to 3x, which means x is equal to log base 7, 6 over 5 plus 5 over 3. So those were with unknowns in your index. Now sometimes you have unknowns involving the log part. So let's do a couple of these questions. So A is log base 3x is equal to 2. Because we've got log base 3, we're going to do 3 to the power of to both sides. So I get 3 to the power of. 3 to the power of log base 3x is equal to 3 to the power of 2. They cancel out. So x is equal to 3 to the power of 2, which means x is equal to 9. If I do B, log base 4x is equal to minus 3 over 2. Because it's log base 4, I need to apply 4 to the power of to both sides. So I end up getting 4 to the power of a log, oops, undo, not writing yet correctly. 4 to the power of a log base 4x is equal to 4 to the power of minus 3 over 2. So these two cancel out. So x is equal to keeps changing. X is equal to 4 to the power of minus 3 over 2, which means x is equal to 1 over the square root of 4 cubed, which means x is equal to 1 over 8. See? I've got log base 3 of x squared plus 7 is equal to 3. Because it's log base 3, I need to take 3 to the power of in both sides. So 3 to the power of log base 3, x squared plus 7 is equal to 3 to the power of 3. These two cancel up. So all I'm left with is x squared plus 7 is equal to 3 cubed, which means x squared plus 7 is 3 times 3 times 3, which is 27. If I subtract 7, I get x squared is equal to 20. So x must be plus or minus square root of 20, which means x is equal to plus or minus 2 root 5. Okay, let's do D now. We have log base 3 of 6x squared plus 13x plus 22 is equal to 3. If we apply 3 to the power of to both sides, we get 3 to the power of log base 3, of 6x squared plus 13x plus 22 is equal to 3 to the power of 3. These two cancel out, so I'm left with 6x squared plus 13x plus 22 is equal to 3 cubed, which we worked out is 27. This looks like a quadratic, so we need to take everything to the left-hand side. I get 6x squared plus 13x plus 22, take away 27, which is minus, plus 22, take away 27, which is equal to 0, which means 6x squared plus 13x, take away 5 is equal to 0. This looks like it's going to factorize. I will try, by trial and error, I'm trying 3x and 2x. I want a positive 13x, which means I want a plus 5 here and a minus 1 here. So if I see, I get the minus 5, I'm getting the minus 5, and I'll get 15x take away 2x, which is a 13x, which means x is equal to a third, and x is equal to minus 5 over 2. Now, you have to be very careful with these kind of questions because they are hidden quadratic questions involving indices, unknowns in the indices. So let's go through some examples of those. Okay, so we've got 5 to the 2x. Now, 5 to the 2x can be rewritten as 5 to the x squared, because x times 2 gives you the 2x, minus 3 times 5 to the power of x minus 88 is equal to 0. So let y be equal to 5 to the x. Then you have y squared minus 3y minus 88 is equal to 0, which is a quadratic that you're used to looking at. Let's try to solve this by factorizing. It looks like it's going to factorize. So I've got y and y, because it's y squared. 88 with a difference, a product of 88 with a difference of 3 is 11 and 8. So it must be minus 11 and positive 8. That gives me minus 11 times 8 gives me negative 88, and minus 11y plus 8y gives me negative 3y, which means y is equal to 11 or y is equal to negative 8. Okay, which means, remember, we substituted y is equal to 5x, so that means 5 to the power of x. 5 to the power of x is equal to 11, or 5 to the power of x is equal to negative 8. Now, straight away, you know that 5 to the power of x can never be a negative number, so no solution for this one, as 5 to the x is always greater than 0. Okay, so that means this one will give you, because 5 to the x is equal to 11, you need to take log base 5 on both sides. So you have a log base 5 of 5 to the x is equal to log base 5, 11, which means x is equal to log base 5 of 11. And that would be your only solution. Another example, similar example. Okay, so 7 to the power of 2x can be rewritten as 7x squared, take away 3 times 7 to the power of x plus 2 is equal to 0. So let y be equal to 7 to the power of x. Then you have y squared minus 3y plus 2 is equal to 0. This is an easy factorizing problem, which means y minus 2 and y minus 1 is equal to 0, which means y is equal to 2 or y is equal to 1, which means 7 to the power of x is equal to 2 or 7 to the power of x is equal to 1. The second one is easy because 7 to the power of what is equal to 1. We know x must be equal to 0. So that's the solution for that one. And this one, because it's not an exact answer, we need to use logs. So because we have 7 to the power of x is equal to 2, we take log base 7 on both sides. So log base 7 of 7 to the x is equal to log base 7 of 2, which means x is equal to log base 7 of 2. So there are two solutions, x equals 0 and x is equal to log base 7. 2. Gets a bit more complicated with this one. So we've got 4 to the power of x plus 5 times 2 to the power of x is equal to 14. Now, the key skill here is recognizing that 4 can be written as base 2. So 4 can be written as 2 squared, and then we got to the power of x, plus 5 times 2 to the power of x is equal to 14. Okay, remember we can swap the 2 and the x around. So this is the same thing, because 2 times x is the same thing as x times 2. You can rewrite this as 2 to the power of x to the power of 2. So these two sort of swap around. Plus 5 times 2 to the power of x. Now I'm going to take the 14 over to the other side because it looks like it's going to be hidden quadratic. So minus 14 is equal to 0. Okay. At this point, we'll do a substitution. Let y equal to 2 to the power of x. Then we have y squared plus 5y minus 14 equals 0. Now, if we factorize this, we get y plus 7 and y minus 2 in the other bracket, which means y is equal to negative 7 or y is equal to 2. If we do the substitution back, then 2 to the power of x is equal to minus 7 or 2 to the power of x is equal to 2. No solution for this one, as 2 to the power of x is always greater than 0. So for the second solution, 2 to the power of x is equal to 2. X must be equal to 1 in this case, because 2 to the power of 1 is equal to 1 is equal to 2. Okay, if you do the log way, you're going to get x is equal to log base 2 of 2, and later on you find out why that's always equal to 1, but we won't go through that now. Okay, 9 to the power of x minus 3 to the power of x plus 1 is equal to 10. So again, we need to write 9 in base 3, so it's the same thing as 3 squared to the power of x minus 3 to the power of x plus 1 is equal to 10. What we need to realize, the second term can be split up. It's the same thing as, so leave the first term as it is 3 to the power of x minus 3 to the power of x times 3 to the power of 1. So we can split the two terms on the index as 3 to the power of x times 3 to the power of 1, which is equal to 10. Okay, what we realize is I can rewrite this first term as 3 to the power of x squared minus, this is 3 to the power of 1 is just 3. So it's just 3 times 3 to the power of x. We just swapped up these two over. And if I take the 10 to the other side, I get minus 10 is equal to 0. So now at this point, I can do a substitution. Let y be equal to 3 to the power of x. And then y squared minus 3y minus 10 is equal to 0. If I factorize it out, got y's in both, and I get minus 5 and plus 2, which means y is equal to 5 or y is equal to negative 2, which means 3 to the power of x is equal to 5 or 3 to the power of x is equal to minus 2. No solution for second one, as 3 to the power of x has to be greater than 0. For the first one, you have to apply log base 3 to both sides. So you get log base 3 to 3 to the power of x is equal to log base 3 of 5. So x is equal to log base 3, 5. One last example that I'll go through is this one. So 81 and 3. Now, using the other skills that we used in previous examples, you'd be tempted to write it as base 3. But if you write it as base 3, you can get 3 to the power of 4x, which gets 3 to the power of 4 to the power of x, which gets very complicated. So instead, I'm going to write it as base 9. So 81 to the power of x can be written as 9 squared to the power of x. 3 to the power of 2x can be written as 3 to the power of 2x plus, because we got plus 2, it's the same thing as times it by 3 squared. So I've split this up into 3 to the power of 2x times 3 to the power of 2. Maybe explain that a bit better. Is the same thing as 3 to the power of 2x times 3 to the power of 2 using the rules of indices. Okay, minus 1 here, don't forget the minus 1. So it's the same thing as, I can write 9 to the power of 2 to the power of x as 9 to the power of x to the power of 2. 3 to the power of 2 to the power of x can be written as 9 to the power of x times by 9 minus 1. Okay, now I can let y be equal to 9 to the power of x. And what we have in front of us is y squared minus, y squared is equal to y times 9, which is 9y, take away 1. So if you take everything to the left-hand side, I get y squared minus 9y plus 1 is equal to 0. And by looking at that clearly, I can see I cannot factorize it. So I need to use the quadratic formula. So y is equal to minus b, which is equal to 9, plus or minus b squared, which is 9 squared minus 9 squared minus, oops, let me just rewrite it properly. So minus 9 squared minus 4 times 1 times 1 all over 2 times 1, which means y is equal to 9 plus or minus 81 take away 4 is 77 over 2, which means y is equal to 9 plus root 77 over 2, or 9 minus root 77 over 2, which means 9 to the power of x now, because y is equal to 9 to the power of x, is equal to 9 plus root 77 over 2, or 9 to the power of x is equal to 9 minus root 77 over 2. Now we need to check that they're both greater than 0. We know that one's definitely greater than 0. Root 77 is definitely less than 9, so this is also greater than 0. So it does work out. So now all I have to do is apply log base 9 to both sides. So if I apply log base 9 to both sides, I get log base 9, 9 to the power of x is equal to 9 plus root 77 over 2, or a log base 9 of 9 to the power of x is equal to, for the log base 9. So let's rewrite that again. Okay, so apply log to the base 9 to both sides. So I get log base 9, 9 to the x is equal to log base 9 of 9 plus root 77 over 2. Or, I'm just going to have to write it here, log base 9, 9 to the power of x is equal to log base 9, 9 minus root 77 over 2. These two cancel out, so all we're left with is x is equal to log base 9, 9 plus root 77 over 2, or a log base 9, 9 minus root 77 over 2. So those two are the solutions. Okay, just one thing right at the end I need to go through is equivalent notation. So if we know a to the power of x, if a to the power of x is equal to n, then that means because we've got x as an unknown and we've got a to the power of, we can apply log base a to both sides. So log base a of a to the power of x is equal to a log base a of n. But these two cancel out, which means you've got x is equal to a log base a n. So this expression is equivalent to this expression. So a to the power of x a to the power of x is equal to n is equivalent to x is equal to log a base a n. Okay, so example, if we have x is equal to log base 10 of 1,000, that is the same thing as writing 10 to the power of x is equal to 1,000. So 10 to the power of x is equal to 1,000. With 10 to the power of what gives you 1,000? X must be equal to 3. Some of these things you can do mentally using this equivalent expression. So another example might be, we've got x is equal to a log base 2 half. That means using the equivalent expression, 2 to the power of x is equal to a half. So 2 to the power of what gives you a half? Obviously 2 to the power of minus 1 is equal to half, so x is equal to minus 1. So if you get confident using these equivalences.